Okay. Right. All right, welcome back, everyone. Our last talk for today is by Professor Trevor Darrrell. Trevor's professor at UC Berkeley here. So it's not far for him to come here, but it is CVPR deadline tonight, so he's making a sacrifice anyway by being here. Yeah, so Trevor is, of course, very well known in the field of computer vision and machine learning, and has worked on issues related to domain adaptation and distribution shift, and has recently received Test of Time awards for his work in using deep learning very early on, using features from neural networks and showing that they're very robust to distribution shifts. So please welcome.
Thank you very much. Ooh, a little bit of echo and feedback. I'm really happy to be here. I think, especially today, it was interesting to see the diversity of talks in this program, in this session. I saw the live stream of Zach's talk, just quite a range. And so I think I'm going to try and contribute to that today as well, by giving you a talk that has no equations in it, right? For Simon's talk, that'll be of interest. And you are probably not going to have any vision people in the audience tonight because it is the CVPR deadline. I don't know who managed to schedule me on the day of the deadline, but I'm happy to drop in. And it was interesting because I found a bunch of slides about our recent work in domain adaptation that I hadn't looked at in a year and are very interesting to go through again. Really, I'm going to be presenting the work of Lisa Dunlap, who's a grad student co-advised by me and Joey Gonzalez and influenced by a few other people, who did a body of work about a year or two ago on combining language and adaptation. So in the spirit of domain adaptation, I think that's what will be fun to go through today. And at the end, it'll tie into the latest work that she's been doing on describing visual differences and sets of visual differences, also using language and vision models. And it ends up having an impact on how we might understand robustness and trying to understand, for example, the different kinds of ImageNet data sets and the divergence of performance we see there. But let's just start from the beginning. And so this is going to be hopefully short, sweet, and colorful. As I said, this will be the counterpoint to the equation-loaded talks. And if I can end early, I'll return time for either discussion, conversation, or overleaf, depending on what you're interested in tonight. We're dealing with domain shift. I've seen the slide be set up by several speakers already. So we've got train, we've got test. We're trying to figure out what's going on. The real world is painful. And the angle we're taking on this problem in this talk, in this work, is how can we use language as an additional source of advice to get out from underneath this problem that otherwise would face you in traditional computer vision settings. And now this is traditional computer vision circa 2022. So I think actually some of these approaches might change in a fully multimodal LLM context, but we can talk about that at the end. And I think even other speakers showed the Landbird and Waterbird data sets. So maybe I don't need to explain them. That's a kind of a cliche and cartoon. And I think you presented it and Zach criticized it. I was working on my papers over at home this morning, trying to watch the talks at the same time. So I agree with all the criticisms of this data set. And I also think it's an interesting data set to try and show some results on. And maybe you can just consider it illustrative, if nothing else. And so, you have land birds, but they might be in front of land, they might be in front of water. And, especially in 2021 or 22, if you just give this to a CNN, try and train a CNN on it, it's obviously going to pick up the spurious correlations. But thinking of it from the perspective, sorry, I deleted the wrong slide there. Yeah. So because the CNN, or if you treat this as just a supervised learning problem, it's really underspecified. It's sort of frustrating because, how does the classifier know whether you care about the bird or care about the background. And that's often a lot of these things. Like there's cases in medical imaging where it picks up on the little piece of metal that happens to have been used on a particular scanner or something, or X-ray device. I mean, these machine learning algorithms are so good at finding spurious correlations. How do you know that's not what you're supposed to do? Well, I think the somewhat straightforward but useful idea is to tell the classifier not to pay attention to those things. Right? So we wanted to start to build models that could use everyday language so that we could tell the model what the signal was and what the signal wasn't in this case. If you looked at the sort of, even today, potentially the standard method for classification, you're faced either with using a large scale foundation model, which could be a model like GPT or Lava, but probably CLIP is still close to the best performing model in some of these cases. And CLIP is this now classic model, which has a lot of training data and good general performance, but does not work well on fine-grained data. So you'd like to train the model to recognize these different classes. If you train it with CLIP zero shot, it's not going to work so well. I don't think I have this slide, but if you then fine-tune CLIP zero shot, you end up overfitting to the data that you have and having the bias problem. But what you can do, and what CLIP is certainly capable of doing, is saying, hey, these are birds, and these are different environments. We have land and we have water. So we see a trade-off evolve. Again, this is maybe 2 years ago, with the dominant techniques being either CLIP or convnets, or a combination of CLIP and convnets where you're fine-tuning CLIP with additional data, and then you get a sort of combination or mixture of these trade-offs. The large foundation models are robust to contextual bias, have a language interface, understand the high-level concepts robustly, but generally didn't have a capability for fine-grained classification. And more detailed specific models, convnets, very high capacity, can overfit to almost anything, but generally overfit often to things that you didn't want. So the main part of this talk is a series of 3 papers that we wrote from 2022 to 2023 called GALS, LADS, and ALIA. And they had the general goal of bringing language advice to vision problems and trying to sidestep some of the trade-offs of interpretability and robustness, which are often viewed, especially from a theory lens, as a zero-sum game, but say, no, actually, if you have an additional modality, you can have additional signal. We want to create interfaces where the user can tell us what is wanted. And so I'll go through these in detail. Roughly, the high-level idea of each of them is to be right for the right reasons. For those of you who are in the explainability community, that's a phrase that refers to a classic paper and the idea of making sure that the evidence you're making a decision from is consistent and the correct evidence. The second paper and the third paper are both on augmenting your training data to account for domain shift and domain adaptation. The LADS paper is going to be doing it in a CLIP embedding, and the ALIA paper is going to be doing it with diffusion models in a pixel space. But I can go a little bit more slowly through each of these. So this GALS, and actually Lisa Dunlop, who again is the author of all 3 of these works, and made all these slides, and also comes out with these great acronyms, GALS and LADS, and I don't even want to tell you that the third paper was almost called DADS, and then we rescued that and made it ALIA instead. But yeah. So we'd like to be right for the right reasons. We'd like to be inspired by interpretability and explainable AI. But we don't want to do that just to feel good or to have some qualitative understanding of a model. We want to do it because it's going to help our performance. And how is it going to help our performance? It's because we're going to turn it into advice. So we're going to turn it into a constraint that not only do I have loss on the task, but I have loss on the support set from which you should have made the decision on the task. And informally here, the model will take advantage of the fact that you say, this is a bird classification task. Please don't bother looking at the background for this. Or maybe you do know the back, so because this is something that it really is context dependent. I mean, if you really want to do land bird and water bird classification, and you know that your training data and your testing data are consistent in IID, well, you want to use the background, right? Because the background will provide a lot of signal to classify the bird. But if you know that you're then going to have a camera deployed in another environment, and you may end up trying to see these birds maybe on an airport runway or something, well, you don't want it to or in fact, in the reverse setting, you're going to be only taking pictures in the air. You don't want it to pay attention to then spurious features. And so that's why it's cool to allow models to have language advice. And the idea of adding language actually was still revolutionary or controversial in 2020, 2021. I think it may not be today. I think the multimodal, especially the large multimodal model revolution has just really swept the field. So it's almost quaint now to say, well, adding language is a useful thing because it's sort of obvious that it is. And so some of these mechanisms, I think we need to go back and redo now with the large multimodal models of lava and whatnot in 2024. That's the virtue of giving talks. You realize what future work there is. And in 2020, 2021, there was a lot of great work, some of it led by Kate in her RISE model, and the earlier work called GradCam, which would try and identify which pixels in an image for an image classification task, and there are other similar models for text and other domains, was salient or responsible for a decision. This was sort of the visual interpretability work. And there's a lot of criticism of that work as a side comment, and much of that criticism is valid. But I think what isn't too debatable is that if you know you want to pay attention to something in the image, or you know you want your model to not pay attention to trees, it's a pretty easy way to enforce that by adding an additional loss on the attention. Tell the model what it should be paying attention to and making sure that it's right for the right reasons, not just right accidentally by happening to find some spurious correlation, but it's right and it's looking at the right things. And it's very much why I have teenagers at home when they do math homework and they're graded on their math homework, they don't get all the points unless they show their work and their intermediate steps are also correct. So especially when you're trying to build a robust system that may generalize well in unknown future conditions, it's useful to try and make sure that the intermediate processing or literally the attention in this case is consistent with what you're expecting the model to do. So we actually have a loss function that's somewhat similar to, oh, sorry, that's coming up in another slide. So the model is very simple. Again, no math in this talk, so you're not going to see actual loss functions, but we just have an additional loss term over the attention head. The attention head comes from GradCam or RISE or something like that. And that's the first place where you get real leverage combining language into domain adaptation. If you have the knowledge that you want something to be constrained, you can use it. A quick question, sure.
Oh yeah, sorry. This is really cool. How do you get the labels, like with the heat map?
The labels with the heat map. Well, you're given the knowledge that the task is classifying land bird or bird, and you're also given the knowledge that there's a concept hierarchy and that these are both birds. Or you're given the knowledge to quote ignore the land or ignore the water. So you're given some knowledge of that form, and from that we have the attention loss, which would be show me the attention with regard to the supercategory bird. So this is the attention with regard to the supercategory, and you want to make sure that it's paying attention to the supercategory when it makes this fine-grained distinction. It's not looking at some random feature in the background.
Okay, thank you.
I guess the question is, you needed to know the supercategory a priori, right? So how do you know that?
Language. That's the whole framing here, is that there's additional information. language provides additional information. So you're given, or the category hierarchy. So how can you take advantage of that in a traditional architecture?
No, I understood that part. I'm saying, how is it providing that? It's just language for the.
It's just the word bird, the text string bird, is used as a clip feature, is used to generate this attention map in a clip representation. So I'm probably not going to go through GradCam, but given a text string and a clip, this clip style model back here, clip is a model which is where you have contrastive learning to train an image encoder and a text encoder, given a series of text features and image features, and a large paired data set of images and strings. It learns a representation that projects these two things to the same location. And by evaluating the label conditional gradient, the GradCam models can show which pixels are actually being used to predict the feature.
Quick question. It seems that the language is a way of imparting the knowledge into the system, but the knowledge seems to be more about the task. So the task is water bird versus land bird, but there's knowledge to say that the super category in this case is bird.
Yeah.
Yeah. Right? So it's the language is a way of getting that information into the model, but you need to know the task to figure out that bird is the relevant.
Yeah, it's an additional it's additional information in the problem statement.
Yeah. Okay.
Right? Instead of giving me a list of images with the label 1 and a list of images with the label 2, I have those two lists, but I also have 3 words. The name of each of those fine grained with a little, I have the class 1, class 2, and superclass names. Yeah. Anyone else? You already have one. You got one per set of slides. I was told. But they're good questions. We like it. Yeah. So, by the way, Zach also was right, and I'm not sure. All of these results are they're 2 or 3 years old. So I don't really want to hold my hat on any one of these charts I'm going to show you, especially because I'm showing you 3 different things. I just wanted to give you the big idea and say some of these ideas are worth re-exploring because they're a little bit old. But we did show strong performance, 10 or 20 points over the baseline, and you would see essentially the model being able to be right for the right reasons. If you would train a CNN, it would overfit, and you would see that it would end up relying on things that you didn't want it to rely on. If you use this somewhat straightforward idea of adding loss on attention, you could get the model to be right for the right reasons, and see good results. And you could also see it in domains where you might want the model to not pay attention to co-occurring things. Like you don't want the model to pay attention to the environment so much when you're looking at a parent gender, or maybe if you're trying to classify different types of meat, you don't really care if there are potatoes in the background. You just want to actually look at the local features, and so you can get this model to work. So this was great, but it wasn't as great as it should have been. Again, this is one of those cases where it still had a hard time. Those attention models are flaky. So we got a signal out of it, but it wasn't the most powerful signal that I thought one could get. It seems like there should be more juice in bringing language to bear. So the next part of the story was, instead of trying to add constraints on attention, let's try and follow the well-trodden path of augmentation or augmentation for robust learning, and see how we can use language-given knowledge about domain shift to improve augmentation strategies for robustness and adaptation. And so those are these 2 papers called LADS and ALIA. And they both have a similar story where we're going to take knowledge. Now here, the language is going to tell you what the domain shift is. The language is going to say, these are sunny images. You might be in a snowy domain tomorrow. Or pay no attention to the runways if it's a plane classification task or something like that. And then we're going to use those language specifications of our expectation of the future environment. I mean, I think there are many cases where you've trained a model. Sarah Beery was here earlier. I don't see her here now, but she may train a model of a certain animal species in a laboratory or in a zoo, but she knows it's going to be deployed in some other space, other place. Now, I guess the traditional vision person's approach to this would be, oh, you have to go out and collect imagery from that place, even unlabeled imagery, and bring it back. But that could be much more expensive than just a description that it's going to be different and it's going to be different in a certain way. Or even that here are features of the current domain that I expect are not going to be consistent in the future worlds. And to do that using language specification. And once you have that, you can then implement it, you can then exploit that in two ways. One, you can do it in a feature space, and that's the LADS paper. And the other, you can do it in a pixel space, and that's the ALIA paper. So the LADS paper does what I said, which is you have a training domain. Let's say you want to do sign classification, stop signs, and other kinds of signs. And I'm here in sunny California, and so I've collected my data set in my little neighborhood where everything is bucolic and sunny. But I might go visit Kate occasionally and have to deal with these kinds of signs. Or I might go skiing in Lake Tahoe and have to deal with these kinds of signs. And we all know that performance will, so now I have a choice. Do I use a traditional discriminative classifier using a CNN and fine tuning? Or do I just go ahead and use GPT or 2 years ago, clip zero shot, right? And the generic model might have sort of unbiased performance. It might work roughly the same in both domains. But you're always, as Sarah, I think, said in her talk, if you really want good performance, you still need data from that domain. If you train on data from that domain, the performance is still better than what you get from these zero-shot models. So how do we try and get the best of both worlds, where we can take advantage of the training data, but not be fooled or not be tripped up by the domain shift? I think at the time, 2021, 2022, this was a standard approach. Let's do image augmentation with VQ GANs. And we are going to come back to image augmentation in the next slide, so I don't want to poo-poo it too much. But at least this version didn't work because VQ GANs weren't good enough. We'll come back and do this with diffusion models in a second. But what was surprisingly effective and pretty simple was to take the semantic geometry ideas that have been around for decades in the clip embeddings, in the glove embeddings, in other kinds of feature spaces where you can take men and women and find a vector in the semantic embedding between those two, and then maybe add that to king, and suddenly you get queen, or maybe I got it reversed so you can subtract it. But literally here I have a training domain. I have where the stop sign is living in that training domain. Let's start with just a clip embedding space for starters. I do have these additional words that I'm given, which are snowy and sunny. I give that, maybe I have this little phrase, but basically these two words are the things that are going to be colored red and green. Please augment my training data such that it's invariant to the distinction between sunny and snowy. Now, in the old days, and I think Sarah also presented a very cool generic version of this as well, we had domain invariance architectures. Kate wrote several of them back in the day. Judy Hoffman also worked on this, where we would take unlabeled data sets and say, here are two unlabeled data sets. One represents domain A, another represents domain B. Let's add a loss that says the model can't distinguish between those two, a sort of a GAN discriminator loss, and use that as a foundation for adaptation. Now, I mean, a lot of us thought that was a really cool idea. I think Zach referred to those as well. And we're all just so frustrated that they don't really work. And we don't really know why, but there's a bunch of papers that we all wrote on those 5 or 6 or 10 years ago. And it was a struggle because those adversarial methods are hard. But this sort of works pretty well. It's a similar spirit, except instead of defining my two domains with unlabeled image sets and trying to build a discriminator that can't distinguish them, I'm just going to use an existing foundation model and like subtract two populations to find a vector and add that to some training data. except I'm going to do it in a more fancy and principled way. Again, there's math underneath all of this, but I'm giving a no equation talk just to prod the gods of theory and Simons. But we have an architecture that looks something like this, where you have an initial data imagery, and you'd like to actually also work for paintings. So you want to essentially hallucinate an image embedding. So we're never going to actually generate pixels. We're going to say, here's the embedding of that image, and I'd like to change it in some way such that the model can't distinguish the embeddings, but can continue to distinguish the classes. Right? I'd like to be able to still distinguish puffins and sparrows, but not distinguish the two different snowy and sunny, or photo and painting in this case, and use the same kind of adversarial approach, but now just in a much lower dimensional pixel space, so it works fairly well. So here's some results of that story. Again, I won't go through the tables of numbers. Seem to only be valuable for current grad students who are within a year of the publication. Like, I don't know. The idea is the trend for me, not the actual performance. But it does work pretty well compared to all the original baselines that we had, and using zero shot or using a previous method called LADS. Here's the, this is the performance of our model. This was a previous method. This was just doing zero shot clip. So the truth still was, even in this era, that we were only getting 10 or 20% boost on just the zero shot foundation model. And you know, the steamroller of just making that better is still an issue. But I was reassured by the comment that I'm going to repeat about that Sarah Berry said, which is still, when you're out there trying to do the kind of work that she's doing, the complete zero shot models still don't work well enough. And so we have to find a solution, I think, still, to how we can train on in-domain data and not overfit to in-domain data. And I think this conversation is still quite relevant. I can't read. I don't want to take a guess at that, but if you're interested, the iClear paper is available to you. This, however, was showing that, so again, we're generating an augmented sample for each training sample. And while we weren't manipulating pixels, given that there's a larger data set, or we're working on a data set where there are images from another domain, purely for visualization purposes, we can go find the nearest neighbor image in that other domain, like in the test, in this multi-domain data set, and see that actually the geometric augmentation, the nearest neighbor to that resulting point is pretty close to something that looks like, to me, a painting that's consistent with the subject matter and content of that story. Yeah, so that was a cool paper. But we were overtaken by stable diffusion, and pixels came back. We were vision people after all, and it just felt like, my gosh, we should, given how well these diffusion models are suddenly functioning as generative models of images, and given the fact that you could certainly condition them to be conditioned on an input image, let's figure out how to add variety and uncertainty and augment our data with language to build a more robust model. Build a more robust model that we called ALIA. And here the idea is, again, augmenting with the same problem statement and same setup, but now seeing whether diffusion models can add additional punch by adding noise to, basically you'd like to have, take a sample, add noise to it, add variation that you expect in the domain, maybe change the weather, change something, but have it be consistent. So this was this ALIA paper, data augmentation with diffusion. You can see how we almost called it DADS, but we didn't. We called it ALIA. I didn't mind all the gals and the lads, but the dads paper was going to make me feel like I'd have to give dad jokes or something like that. The basic architecture here is to take advantage of the burgeoning capability of captioning models. You have some of Sarah Beery's training images from Wilds here, and they're few and far between and a bit idiosyncratic. So can we take one of these great pieces of source data and add variation to it so we can have more robust classification? So we can take a captioning model and we can see the caption can generate, sorry, we have the original image, which has particular content, and then we can generate a summary of that, these images. And sorry, we can generate captions of these images and then summarize those captions to get the general gist of this environment. There are a variety of different kinds of things that happen or don't happen, weather conditions. And so we can use that in another, as conditioning information to add variation. So we may see something in one image, let's say, oh, add that to this image. Maybe there's a lake in some environments, maybe there isn't a lake in that environment. So we could take a training image and then ask a conditioned diffusion model to say conditioned on that original image, and here's some text variation. Let's make this one, let's make all these near a lake. So you can see we take the source images and we ask a diffusion model to add some water. And so we get kind of a near noisy example that is useful as an augmentation strategy for building a robust classifier, except when it's not. You know, sometimes you get something that truly does look broken. So we have the equivalent of our story, which says, but the model has to stay close enough to the original distribution. So we do have a classifier that says, is this still basically the same kind of image? Does clip still say that it's still the same kind of scene? And so there's some outlier rejection strategy. It's a little bit ad hoc, I will admit. And so I want to do this slide first because it shows the background. Maybe I should have started with this to say that maybe 2 years ago, it was pretty common idea. Everyone thought that this algorithms like cut mix and randog were just going to save the day, because on ImageNet they do really well. And it's just like I take some data and I augment it by making random permutations, taking half of one image and half of another image and adding that to the data set, which scares the thing out of me. I'm like, how could you just randomly permute your training data like that and believe that that's still a valid member of the class? Nonetheless, that's what people did. I think they basically would do stuff that would work on ImageNet, and then we get higher up on the ImageNet leaderboard for unsupervised segmentation. And this is why none of these things ever work when you go to a real domain, because you go to medical imaging and it doesn't work to take one half of one lung scan and copy in another half of a lung scan and it's still the same diagnosis. Okay, it works with ImageNet. So I'm not sure that nothing's ever going to work, but a lot of the stuff that was leaderboard driven, ImageNet focused, like super rapid publication work, overfits quite literally. Even it's ironic to build robustness algorithms that overfit to data sets, right? So this is what we had before.
Maybe 20 years ago, when you were complaining about overfitting to ImageNet.
Yeah. Well, I'm still here. Life is good, but the problems are still here too. So this is what some of the baselines were doing, and this is what our algorithm was doing. Still trying to take the source image. You could take a diffusion model and just say, generate text and try and use the diffusion model to generate additional images from the category. It was surprising that worked, but it's doesn't seem to me like this would work for fine grain recognition. But that's a whole nother story, how we can get signal out of diffusion models. And so we could take the original source image and condition it with some additional text that was extracted through that process that I mentioned earlier, and maybe change the background or change the viewing condition or change the weather as appropriate. And that did help improve performance on, say, a baseline method. Here's Cub. If you added these things that worked for ImageNet for augmentation, some of them hurt, some of them helped, some of them helped a little bit. Ours was consistently much better than that. And sometimes our alias stuff was even better on iWildCam, I would love to have Sarah's comment on this. Like, it was better than adding real images. That's a high bar. And as I said, we still had to have a model to make sure that it didn't completely go haywire. Sometimes the diffusion models just go off the rails and we have to figure out why. Okay, yeah?
Elaborate a little more on that. Well, what does that really mean?
That means that this is adding additional, so we start off, I forget the actual numbers, but I'm just going to make it up and say there was 100 training images per fine grained class. And now these guys are adding maybe another 50 images that are formed, or maybe 500 images. Maybe you take every original image and augment it 5 times, add it to the training set. And we've done that here. We've added 500 images. As an oracle or a baseline or just a point of comparison, you could take 500 more real images. And so there's no formal proof that they'll do better or worse than these augmentations. If you had a really good augmentation strategy, there's no theoretical reason you couldn't do better. You could have a synthetic model that's better than the real world, I guess.
I'm just trying to grasp on the intuition of that. I mean, the baseline for me is that we augment so well that it matches the reality. But it doesn't mean, how could it be?
I mean, if I have a bad source of real images, I just take the same image 10 times. I don't know. It's a good question. Maybe there's some statement we need to make about the distribution of the real images. I'd have to go back and reread the experiments. Yeah, and I'd refer you to this was a iClear paper 2023. So I think it's like if you just take the next 500 images out of the data set, I mean, there are error bars here, so there's some signal. But I think if you had so I guess the story is the diffusion model could be anything. It's like, who knows what's in the diffusion model? The diffusion model could have been trained on every image that's ever been seen. So it could be we're secretly just decoding more images out of the image model. So that's probably the theoretical story here, that there really is some signal in those diffusion models. When you ask it to generate these images, they're almost as good or better than, it might pick a really exemplary bird feeder, or the kinds of images it's going to give you. Yeah, but I agree with you. That's anyway, maybe we should just, let's make the error bars bigger and then could be the same. I don't want to stand too hard on that one. So that was the main part of this talk, but I still have a few more minutes that I'll go to the coda of the talk. I think I'm trying to end around 5 or 5:05. 5:05. Okay. So you got the story there. And I really do have to acknowledge all my awesome co-authors, especially the fourth one there. This co-author was a great student to work with. You might recognize the last name. She's wonderful. She's at Harvard now as a grad student. So the punchline of this was, if I had the language advice, look at all the tricks I could deploy. Maybe I could constrain the attention in a XAI story. Maybe I could use clip geometry to generate some additional samples. Maybe I could use diffusion models to generate additional samples. But someone's given me that distinction. I guess it's never going to be fully AGI'd here. But wait, there's more. Here's the coda for the rest of Lisa Dunlap's work. The same first author now. I'm really singing her praises. She's not on the job market this year, maybe next year. But invite her to come give a talk at your institution. I also want to just highlight the other co-authors. Oh no, there's automatic advance on this slide deck. Collaborative work with Stanford. Yuhi is a student of Serena Young's at Stanford, and other co-authors from Berkeley. And here's where we tackle that problem in very recent work, the last year or so, of if I tell you here's 2 different piles of images, how could you figure out what the difference is so you could put it into a system like what we just described? Again, don't expect any equations in Lisa's slides. These are Lisa's slides. I love them. I respect them. This is going to be a very visual part of the talk, but we're still talking about these. This looks like domain adaptation again. I didn't remove all the animations, so it may advance without me. But you get the idea. I should probably move fast here. You get this circle, right? You might be, and this was actually the data set I really wanted to work with for a while. These are, I think these are Airbus, these are Boeings. All the Boeing airplanes are in the sky. Then there's Airbus, and all the Airbus images we had were taken on the tarmac. And so you definitely get a classified overfit, right? So how could you realize that if you did that, you would notice that the model was failing on all of these, for example, Airbuses that happen to be on the sky, whatever I might have gotten at work. But you need a person to look at these images, figure it out, do that loop, and so on and so forth. It's animating for me. Maybe it'll animate in the next minute. I'll just do it. That's a bit of a spiral. And almost everyone doing ML research is up in this quadrant. Can't see the box, but it's interesting how projectors are so different than monitors these days, right? There's a faint box here. And actually down here is probably where we think all the action is to help things in the real world. And very little theory or algorithms, present talk accepted, seem to hang out down here. So that's what Lisa's been working on for the last year, is trying to do something that can solve this problem. And kind of very much using all of the standard tools and the zeitgeist of the day. Because we may just want to discover distribution shift. If I give you two sets of images, for example, if you care about image robustness, you know that ImageNet is a very famous data set. And there's an ImageNet v2 that was from Ben Recht and colleagues. And interesting robustness stories about the difference between these. You'd think they were the same, right? They seem the same. Can we automatically figure out their difference? Or maybe we can do it for diffusion models. Different companies have different models. They give you different answers. What's the difference between V1 and V2 of stable diffusion? Can you find those differences? Or just other forms of data analytics? If some psychiatrists, some psychologists tell you, or some psychiatrists, that these things really have a certain property, these images, what's the difference between the things that people click on and the things that people don't click on? Can you automatically discover that? That would be cool. So it turns out this general problem is sort of underexplored. We called it set difference captioning. And the problem statement is, given two sets of images, can you find properties that reliably discriminate these two sets? There's a version of this problem statement that was done in text that was earlier work by some of our colleagues. And there's a version of this problem that's done for single images that was another one of my students worked on about 5 or 6 years ago. But other than those two works, there hadn't been too much out there. So how do you find these differences? It's a challenging task. There's also very little time left in my talk, so I'm just going to go forward. You can imagine, how do people do it? You'd probably generate hypotheses. You look around, look at a bunch of images, come up with some ideas, and then test them. Come up with a hypothesis, test the hypothesis, create a probe, and so on and so forth. So how's a grad student going to do this in 2023 and 2024? Wait for it. You ask GPT, right? So there's not a lot. The one reason there's no math in this talk, this part of the talk, is there's no math in this. I don't even know. It's not even totally clear aside from the idea of having a two-stage process that follows human intuition. Maybe the results are all just the data and the empirical evaluation in this story. As it turns out, if you do what I just said, it kind of works. You can explore different mechanisms, and there's also, this paper is a nice contribution because it has it assesses a taxonomy of different strategies you can use for step 1 and step 2, and evaluates them, and so on and forth. Also proposes a data set. But basically, since I'm probably going to be pulled off the stage by Kate in a few more moments, let's use the state-of-the-art tools to look at two sets of images, propose a set of predicates that might generate distinctions, then rank them and see what happens. And so there were 3 different approaches. You could caption things, you could just use VLMs, or you could do the sort of clip geometry for both the ranker and the proposer. And I mean, just to make any traction on this, you have to define a data set, come up with some ways of assessing it. So maybe that was the cool part of, like, here's a data set of subsets of ImageNet where there's a single difference that many annotators would agree with. Or maybe here we have people practicing yoga in a mountainous setting versus people meditating in a mountainous setting. Now, if I just showed you one of those, like 1 or 2 images, it's actually hard even for a human. You have to study this for a while to find that difference. And so the VizDiff model, which was a CVPR paper this past summer, works pretty well. And turns out that the architecture that seemed to work, and I think this is purely experimental and I have no confidence will stand the test of time as underlying architectures change, was use a captioning architecture at the beginning, take all your images in, run them through a captioning architecture, and then use a feature analysis model, like a clip-based model, to do the tests. So generate hypotheses based on captions and what you see a state-of-the-art captioner do, and then generate predicates around like clip-like descriptors to see if you can find a way to classify the 2 different sets. Here's some results. Fresh sushi with salmon topping versus fresh sushi with tuna topping. We're 2 different categories. And here are the kinds of outputs of the model. Not exactly right, but pretty close. You could find salmon and salmon topping, but we didn't see tuna, I guess. 1 minute. So I'm just going to end with the ImageNet v1, v2 story because it ties into robustness and that ties into adaptation. Again, there's ImageNet v2. It was created by Ben to try and be identical. If you look at it quickly, it looks identical. It's wonderful. But then they find all of these stories about even just with these 2 things. You train on one, you try and test on the other, you don't get the full thing back. What's going on? How do we undo that? And I'm not sure we're answering that entirely, but you can use this VizDiff tool to go in and systematically find differences that exist between V2 and V1. If you just run it systematically over the data set, you find things that turn out to be different. And here's the punchline, which is more fun. If you look at the whole, if you don't look at category by category, you look at the entire data set, the phrase that comes out of our CVPR paper is, the new one is more Instagram. What does that mean? I don't know. I have to ask my kids. I guess that's what Instagram looks like. And it looks different a little bit. And is that surprising? Well, there is a difference between ImageNet v1 and ImageNet v2. It was V1 was collected by Fei then. V2 was collected by Ben then, Ben and company. And that's the popularity of Instagram. So Instagram didn't exist back here. I guess these were all Flickr images. And so it's an interesting story that, yeah. And we can also do it. Not only can you analyze data sets, we could also analyze algorithms and see why a particular model, like a particular version of ResNet, might make why it fails. And you can just take all the failures, run it through the model. And here it tells you the misclassified images have humans interacting with objects. And it's a pretty good thing. So this is like maybe putting some visual data analysts out of work. And then you can use that to now go out and collect more data, train something better, and do great work. So that's the story. We had a bunch of ways to do adaptation with language, and we had a way to find language from differences of sets, this proposer and then a ranker, and that's it. Thank you.
Very general question. So, I mean, it's amazing actually what you can do by leveraging language in these cases and then first. So, how much more do you think you can do with that using language?
Well, I feel like
is there a limit to what, I mean, or are there more complicated things that you guys are thinking about using language?
I mean, I'm not sure. I don't know what the limit is. I think one thing that's really interesting that's sort of aligned with what you're asking is, will language and non-language converge? And I think there's an interesting line of work of as we get more powerful models in each domain, it does seem easier to align them. Like when you had really poor models, like SIF descriptors for images and like just like bag of words for words, they were so far apart. But as the models themselves are getting very, very powerful within individual domains, like diffusion models generating images, even without text, or text models just on all the text that's ever been written, it's hard to find cases where you can say, here's something that a text model definitely doesn't know about the physical world. Every time I've tried to do that in the last 3 or 4 years, 2 or 3 years, I've failed. If I said, oh, I'm pretty sure text models don't know about scene graphs, or text models don't know about depth ordering in scenes. If I set up a question of what's more like, given the following geometric relationship, what's more likely to be closer to me, the remote control or the microphone after I tell you something about, and you think, oh, that's something where the text models wouldn't know, but they do. It's surprising. It's empirical finding. So there's a conjecture, and I think I'll quote Philisola for this. He had a position paper at iClear called the Platonic hypothesis. So it's like, and we have a paper that isn't quite as articulate as his, that also kind of touched on the same idea. But it's this idea that maybe as the models get more powerful, they're basically coming close to something that's isomorphic with each other or the real world, whatever the real world means. So that's a nice story.
Hey.
Thanks.
Oh, there's more.
Sorry, I know I took up too much of your time, but it was all such a cool talk.